the sixth World Conference, Complex Conference. Donc, we have 5 presentations in this session. It is plenary, this parallel session. We can start. I am Abdelhadi Al-Basha from Qadi Iyad University. I'm glad to be with you and to chair this session. We can start with the first one, presented by Sir Mohamed. Donc, Sir Mohamed Hibti. This is about propositions for measuring the complexity of probabilistic safety assessment models. You can start, Sir Mohamed. We have 15 minutes for each presentation. You can start. Thanks.
Okay. Thank you very much. Thank you for this nice introduction, and thank you for being here for this session. So we have a lot of presentations about complexity. One of the ways to understand complexity is to measure it. Well, this is what we try to do in this work. So I'm talking about probabilistic safety assessment, which is a tool. So I will go very quickly because of the time. This tool is something used in a lot of risk industries, mainly in aerospace and aviation, in nuclear power plants, where this activity is a mandatory one. The other industries also use this kind of tools to assess risks. And the idea is to estimate risk by computing the probability of having undesired events. And these tools, the PSA, provides insights into the strengths and weaknesses of these plants or these industries. So mainly we use this kind of methodology. So we have event trees and fault trees that express all the scenarios that are triggered by some initiator and go to some outcome. This outcome, in our case, may be the core belt in a reactor, the core belt in a nuclear power plant. So we have here event trees. So this part, you have the event trees where you have this kind of missions that we test. If they succeed, they are in green, otherwise they are in red, and this express their failures. And then their failures are expressed like this in what we call fault trees. These fault trees are only big Boolean formula with leaves are charged with some probabilities that express how likely some component may fail. And when we express this, the very ultimate entity that we have to compute is something like this. And just to show you how much this is dense, how much this kind of models are very, very complex. Now, what we try to do is to see all the complexity issues that we may have in our discipline or in our models. And I will focus on this one, on this technical and computational aspect of complexity regarding our models. The other are also perspectives on complexity, but we don't deal with them in this presentation. So there are a lot of complexity measures, and whenever we talk about computational complexity, we convoke somehow Kolmogorov and Chaitin algorithmic complexity. We have a number of complexities that we use that are not really computable. And there is this guy, Hector Zenil, and his colleagues who did a very first complexity calculator that works in the sense that we can capture in real numbers the complexity. So we tried to use it in our previous work, but the computation of the complexity itself was very, very challenging because the time needed to compute the complexity was very high. So we tried other measures, And we wanted to know what defines complex model, what characterizes it, or what characterizes its complexity, and how can we quantify it or measure it. So there is a small paradox here, because the bricks we have in our model, in our fault trees, are only logical gates, which are quite simple, but these simplistic operations can lead to a very high complexity. So I'm going to go to the different ways of looking at this complexity. So what we come up with is that there is ways to compress information without losing it. And the idea is that to apply some techniques to the structures we have to get some information in a very compact form. This is what we call a zoomable PSA, where we can zoom out and zoom in to capture the very detail of the model, but we also can go and zoom out, and then we have a more simplistic model for computation. So sometimes I will just go to a small remark here, is our complexity may be a computational burden, but at the same time, it expresses how resilient our systems are. And the very difficulty we have in our models is that we apply a lot of defense in depth barriers that prevent having accident, and these barriers translated in a very huge combinatorial aspect in our models that make computation very slow. So we, in this paper, we try to identify a lot of families of complexities that we can compute. And the idea is to compute them very quickly to get an idea of our complexity. And the objective is to look at all these families. So since I don't have time, I will not go to the description of these families, but these known, very known families of complexity measured from different areas. And the last one is something with okay, go this way. I'm sorry. So the last one, I mean, the graph translation of fault trees is something that allows us to use a lot of metrics of graphs, and we had this intuition that this metrics may very likely to represent the complexity of our models, but we was wrong. It turned out that this didn't help very much in our problem. So we did also something very interesting inspired from biology, which is the idea of looking at the biological entanglement of components of our systems. And this, go to some, so this is a representation of some selected metrics. So these are the selected metrics that we come up with. So we have the size and the depth of the fault trees. These fault trees go down with traversing a lot of gates. We have block coupling, which means how events are shared by different independent fault trees. And we have what we call the signature overlap, which represents interaction between repeated motifs. And logical alternation is the aspect of traversing fault trees at each time we alternate between OR gates that create a lot of combinatorial and AND gates, which represent system in series. After that, up. So we did an experiment. So the idea, we wanted to see which complexity measure follow the time of computation of our models, considering a solver that we are using. And we had three kinds of families. This, what we call gate-based families that express systems. The other express sequences with a negation here for all the missions that are in success, but also what we call consequence trees, which are a kind of aggregation of a lot of sequences that go to some outcome. So then we did this experimentation, and we tried to compare as a proxy. We used the times for the solver, and here in blue you can see the solver time, and we wanted to see which of these metrics evolve like the computational time of our models. And what we found out at the very end is that depending of the nature of the computation, meaning sequence, consequence, or gate, the shaping is different, or the evolution is different, which means that there is no one metric that may be universal for our models. And this is one of the takeouts of this work. So here we have the same thing with the logical alternation effects with gate-based models. And finally, the consequence-driven models that considers here the entanglement I told about, the entanglement in the biological sense, but not in the quantum sense. So from this, we have this let's say this table of metrics that can be used to predict the complexity of some model or of some computation, but there is, as I said, there is no one that express. Okay, so the conclusion is that we do not have a universal one, but we can have one per family, which is very interesting. And at the end, we will use these metrics to try to send in parallel computations with a kind of balanced complexity measures. The idea is to send different models to parallel processors, but we need to have we need to have something balanced to not have all the complexity supported by one node and the other maybe with very less complexity to handle. And one of the principles we wanted to use in this work is applying simplicity principle, which is something coming from neurophysiology, which is the way the brain do simplification in the real world and process a lot of information, made in them sample without losing too much. So we wanted to use this kind of principle to tackle our complexity and to tackle the way we look at our models. Thank you very much.
This is Ioana from University of Chile. We have this work entitled Emerging Polycentricity in Symmetric Cities, from agent center assignment to evaluating urban dynamic. Thank you. Thank you. You can start your presentation.
Thank you very much. Is this working?
Okay. If you could be closer.
Yeah. Sorry. So hello everyone. Thank you very much for being here. Today I will be talking about emergent polycentricity in synthetic cities, and this is from an agent-centered assignment to an evolutionary urban dynamics. So essentially, we look at cities and how they develop. So why should we study the shape of cities? Well, essentially, in the global crisis, urban areas are a major contributor to greenhouse gas emissions, but they also are massive activity producers. And I mean by that, economic activity producers. Also, around 70% of the world's population is expected to live in cities by 2050, which is actually a 55% increase from where we are today. So you can probably think that predicting these urban growth patterns is quite important for us to build better strategies and better, smarter cities for the future. And the way that we do this is by modeling these kind of strategies, so we can capture urban structure forms and how they evolve, and essentially just monitor them over time. So this is a bit of an interaction loop. What does shape our cities? So essentially we have obviously the land use, how it is used, and how everything is spaced around. Then we have the transportation network that is on top of it, and then obviously the community that produces the activity within the city itself. This is a continuously interactive loop, so we have the transport that gives us accessibility. The accessibility produces the land use and more developed land use, then the activity that happens within that area, and so we need better transportation for accessing those areas. So we look at urban structure as an emergent outcome. As you may know, cities do evolve through a mix of top-down planning strategies, but also local individual decisions. So we can think about them as being driven by congestion. And also, historically speaking, if we look at a very small village, we think that, it's probably going to have a main economic center, but then when we look at the bigger ones, you would probably intuitively think that it's going to have more just because the population grows, there are more things to do within the city and so on. And based on that, people choose where to live or work based on a trade-off between wages, distances, proximity to amenities that are important to each one, and also congestion, how easily accessible it is, their workplace, the house, the places where they want to be. But as economic centers become more crowded, the commuting costs increase, so this could reduce their attractiveness. Nobody wants to stay in traffic a very long period of time just to get to work, and when that sort of threshold does happen, probably most people will think like, oh, okay, maybe I either need to move out or find a new workplace. This feedback between the individual choices and the congestion shapes our spatial organization of activity, so essentially the congestion drives the urban development, and so planners tend to kind of absorb that within their planning strategies. And we try to model these dynamics following the framework proposed by Barthelemy in 2014, which I will be talking about in a little bit. So this is a bit of a positioning. It's a fairly heavy slide. It's not, it's very important, but I will be very brief with it. So we look at urban spatial structure and polycentricity, a bit of economic theory, the spatial interaction and location choice. This is how people make the decision of how to move within the city. The scaling and complexity approaches, which are quite important because we try to map these behaviors to a more overall urban system and a bigger one to see how we look at the system in general. And then the dynamic and evolutionary frameworks, which is the basis of my proposal. And the aim of this work is to examine how the scaling behavior depends on the modeling assumptions that we have made or previous people have made. And we study the role of these feedback loop and updating dynamics in how they shape the city itself. For the scope of this project, I will say that we do focus on car-based commuting and the congestion effects of population. So when I say congestion, I mean the traffic flow of people, not necessarily of car on a road. We do work within a synthetic city with a simplified spatial structure. There are no rent effects considered, so I'm not looking at where people choose to live. I'm only looking at where they choose to work. And there is no explicit transport network of land use dynamics currently. So, scaling an urban system, we know that many properties of cities, they vary systematically with population size, as any organism does. There are empirical studies that show urban quantities follow a power law relationship with population, which is what we try to link back to. And this relationship can be expressed as an urban quantity. That is y, and the n is the population, and the exponent beta, which characterizes how different aspects scale with the city size. For example, sublinear, linear, or superlinear. This can be activities, this can be networks, this can be infrastructure, it can be anything. And each part of it has a different behavior. And this perspective, we can also extend it to the urban structure as an urban quantity and related to population, the population to the number of centers. So these are some initial results that I'm presenting here. Based on the original framework, they looked at the US cities, and we can see this is an inverted relationship that I'm presenting. So instead of looking activity centers to population, I'm looking population to activity centers for simplicity of the axis structure. They looked at the US cities and they said, oh, well, the more population it is within the city, and as the population grows, the centers also grow, but not at the same rate. They grow a bit slower, which is quite intuitive to say. But when I look at a different system, and this is the second and the third scaling law, we can see that it behaves slightly different within the UK system. So in the middle, we have density boundaries. So not essentially looking at boundaries of cities, but at density aggregations. And on the last one, we look at travel to work areas, which are bigger urban areas, and they are the ones that kind of skewed our results at the beginning. So we were thinking, oh, why does that happen? So to look at this in more detail, to try to explain it, essentially, we have a model formulation, and we have a spatial setup. So we've got a synthetic circular city. We have randomly placed centers. Those are where people work. The agents, and then the wages for each center. And then we also have a utility formulation where agents are initially assigned to a center with no congestion. That maximizes their current utility function. That is looking at Z, which is based on wages and the commuting cost. Now, the commuting cost we formulated using the Bureau of Public Roads formulation, which was initially in the paperwork. So we look at the distance, the cost it takes to travel, and also the flow of people currently at the center, and then we have some network-specific parameters that I am not currently focusing on. And the simulation is set up to iterate until equilibrium is reached, and then it runs across a number of different city sizes to simulate the scaling behavior. Now, to do this, we kind of turned it into a simple assignment game. So essentially, following the original paper, we assigned it as agents are introduced sequentially in this city. So if you think about a very empty city, people stand in line and they kind of step by step are introduced in the framework itself. Each agent selects the center that maximizes their utility at that point in time where it is introduced in the city. And then once it's assigned, the agents do not reconsider the choice, so they never go back to it. The emergent outcome is that the congestion does reduce the dominance of a central location, and new centers appear as alternatives, become more attractive, but also this kind of makes it organized into a hierarchical activity of activity levels, meaning that the first center that was active at the beginning will always be the most attractive center, and yeah, it just emerges from the order of agent arrival. So then we try to think about what alternative assignment dynamics we can implement here, and a city will never be completely empty. We can never start from the beginning, so we need to start with a population that already lives inside of it. So we have two potential reassignments. So in the original one, we were considering growing population. Here we worked with a fixed population, no new people coming within the city, no migration. So we propose a synchronous update, so essentially all agents update at the same time if we look on the right-hand side, all the colored people, they basically update their strategies at the same time. And it's based on the same congestion state. They re-update at the same time step and change strategies all the time, and they iterate until equilibrium. Now, equilibrium is never reached because it keeps oscillating in this case, which I will talk about in the results. And then we have an asynchronous update, which is a partial adjustment. 1% of the population updates at each step. This makes for a gradual adjustment over time, and this also changes both the population assertion and the update rule for the resulting structure. So this is a little bit about the scaling behavior in the results. We can see the original UK scaling, and then the bigger graphs are actually the sequential update, the original framework, and then the asynchronous update, so partial updating strategies of agents. And we can see that it sort of follows the assumption of the behavior that while population grows, the centers also grow, but slower. However, the synchronous update does result in overadjustment and instability due to oscillating. And we can see that the emergence of scaling does depend on gradual path dependence dynamics, and it also is very dependent on how we define these dynamics. So to take this into a bit of a different direction, we tried to introduce population games. I will try to be very brief about it. But essentially, we have groups of populations of agents that are matched within different groups. They play the game. Each agent chooses their strategy based off the fitness, and then it follows back into the loop of population is playing the game again, groups, and so on. This is a little bit of the framework, but essentially it's formulated in the same mathematical model. So we still have the utility associated strategy. The only difference is that we introduce a replicator dynamic, which means that people choose their strategies based on what other people have done around them. So if my strategy is better than my neighbors, they're probably going to change because I am making more money. And this is how it reaches equilibrium. We can see a continuous behavior and a state of where it kind of tapers off into equilibrium state. So the scaling behavior under this population dynamic is actually very stable, and it does follow the expected behavior in the original paper, which is good. We like that because we can use this framework as a follow-up to try to explain a bit more of why that difference in unit happens. But we can also look at how we define those activity centers because it's also quite important. So defining the activity centers is essentially anything between the lines that we can see on the graphs or above the red line. We look at the biggest center with the most population that works at there, and then we have this alpha threshold, row 0, which is the one that kind of gives us the cutoff point where we would consider a center to be active. So when comparing these results to the previous models that I mentioned, we can see that in the sequential and the asynchronous, they kind of behave very, very similar. However, the population gains in the one that kind of stays stable throughout the whole experiment, and then the synchronous one we don't really consider it because it ends up to be an inverted scale result. This is a bit about the future steps. I'm not going to go into it too much, but I am hoping to introduce a bit more of a grounded network and actually look at the agent heterogeneity. So because I'm using population gains, I can now look at type of jobs, industries, and so on and so forth. So introduce a bit more complexity into the agent dynamics and explore a scenario-based intervention. Thank you very much.
Continue our presentation with Mr. Jiří from Calzati to present your work and
Okay. So my name is Jiří Nedomlel. I'm coming from the Charles University from Prague. I'm a theoretical biologist. I'm interested in adaptive systems and their resilience and adaptivity. And in this talk, I will talk about simple principles. It's a really conceptual talk. The message is also simple, so I hope we will have good time for questions. The basic question here is, can dissipative processes, thermodynamic dissipative processes, drive complexity? And how can we measure it? I'm looking as a biologist, at an organism, but you can look at any self-organizing unit. If you are from different areas, you can think of maybe companies also. So the starting point for me is classical thermodynamics, right? Non-equilibrium thermodynamics. They basically state that there is dissipation, thermodynamic dissipation increases entropy in an isolated system. And what an organism needs to do in such an environment, it needs to maintain its steady state. It means basically exporting more entropy that it produces by its metabolism, and plus imported entropy by what you consume. So basically, in plain words, you consume food, you burn it, and the entropy must not exceed the entropy that the imported entropy, and the metabolism must not exceed the exported entropy. Otherwise, you will dissipate. And for measuring the complexity, we need to find the right measure. I'm saying, is dissipative process driving complexity, but how do we measure it? So there were a few attempts before in biology also, especially by Daniel Brooks and E.O. Wiley, and they have suggested to measure entropy or information of the complexity. But there are few attempts, and there have been few attempts before, right? For example, equalizing entropy and information. But they said, you cannot make entropy or negative entropy equal as information. You have to say some maximum entropy. So in this graph, you have Smax, which is maximum entropy. And it's the maximum possible entropy of an organism if it would completely dissipate, move to equilibrium. So the information, the organization of the organism is basically the distance from the maximum entropy. And the distance could be the difference between the maximum entropy and the actual entropy of the organism. And they say there should be a paradox, but it's apparently dissolved when we change the maximum entropy. The paradox could be, why, if we have fixed maximum entropy, how can an organism grow, or how can it evolve? It would have to decrease the actual entropy, but it's increasingly more difficult. The solution to this paradox is simple. It suggests that the maximum entropy is growing. So as you increase the number of particles, you're growing by increasing the number of particles. The maximum entropy also increases because it's defined by the number of particles and the number of configurations that they can achieve. So, where is information? It's again the difference between the maximum entropy and the actual entropy. The only flaw is that you cannot choose just any entropy. They suggested Shannon entropy of the genetic pool of or the genes of the organism, but I think this is not correct, and I think we should only use the thermodynamic entropy, because only the thermodynamic entropy is directly linked to dissipation. So what's missing now? We have made a model, what does the organism need to do thermodynamically, but the purpose of this talk, does it drive complexity? I suggest we should look, what does the organism need to do in order to survive, to sustain itself, and to actually grow in complexity, and how does it regulate? So this is the main question. Before I go to the actual process of growing, I suggest that we move on from simple educative maximum entropy minus actual entropy formula that was suggested by Brooks and Wiley, and change it to a more exact one. And here's a plot that I will be using as an illustration. So imagine the world is this plot. It's a simplified world, a 3D, 2D plot on the left side, and you have particles there. Yeah, they have only red color, but just different brightness. The brightness correlates to the energy level of the particle. So the darker colors are lower energy, brighter colors are higher energy particles. Here on the histogram, you can see the distribution of the energy levels. So they are actually following, some of them are following the Boltzmann distribution. Why some? You can see the dark area. I call it desert, really for simplification. So the dark area without the circles is desert. And this corresponds to the blue distribution, really. The Boltzmann distribution, they are completely in the equilibrium. Yeah, they are completely dissipated. And there are two circles, they are out of equilibrium, they are far from equilibrium, they have higher energy. This corresponds to the red particles on the histogram, they have high energy. And I suggest that information would be calculated as a divergence, scale of divergence, from the equilibrium state. So basically, instead of just saying maximum entropy minus actual entropy, you need to calculate per particle difference of the probabilities, which are calculated from the energy levels from the histogram. So you can look at each particle by energy level, then you calculate the probability of the energy level, and just put it in an equation, which says basically the divergence, which is simplified distance from the equilibrium. And that would be correct, no matter if the equilibrium is with equal probabilities or it's a real thermodynamic equilibrium with Boltzmann distribution. So I have come up with this information definition. So it's very similar, just a little bit more exact, and this is what we will call the complexity in this talk. And we will look at it as if it is growing. We have E, or I, which is information, and epsilon is environmental information. It has almost completely the same formula. It's just, I just want to differentiate information of an organism, which I'll call I, and environmental information, which is epsilon. And I will make a statement that the drive of the complexity of an organism depends only on the information of the environment. Which I will just show in a brief, in a minute. One more advantage of my formulation of information is basically directly proportional to free energy depending on the temperature. So it's not a subjective information like Shannon information, but it's really free energy that the organism is consuming and depending on. So now what's happening process-wise, what's happening in the organism? So I suggest there is a process that we call exploration. Each organism is exploring the environment for resources. What the resources have, they have free energy, which is information. So imagine this is a 2D plot. It's a really like world in 2D with particles. And on top of that, there are some lines here which illustrate a simple fungi. Yeah, imagine the organism, the hero will be a fungi. So it starts in the bottom left, and it's a little bit growing and exploring the environment. Yeah, so it starts in the desert, it really has low energy, and then it goes through the environment, basically eating up the particles. So exploration in the simulation and in my talk is a process of growing and consuming particles with some energy. So then you have a subset of the particles which are consumed by the organism. So you can calculate the information of the subset of the particles and compare it to, for example, the information of the environment. So exploration is driven by a rate of exploration, which is here alpha. So basically the speed of how does the fungi grow, how does it explore, is driven by alpha. So here we have already a driver or some rate of exploration that the organism needs to decide based on, I will say, the environment. Another process that is behind every physical process is dissipation. So these are the only two processes that I model, exploration and dissipation. So dissipation has a steady rate, beta, that takes all the particles in the subset of the organism and moves them to equilibrium. And the rate of moving to equilibrium, if it would be 1, it would be completely in equilibrium in one step. There are discrete steps in the simulation. But if it's something between 0 and 1, you have intermediate dissipation. And I will show a graph how this complete dissipation evolves. Okay, so I suggest the information can be put into an equation which balances the exploration gain and the loss from the dissipation. And this is a very general equation that you can talk about organisms or organizations or companies also. But really, let's stick back to biology. The exploration gain is basically the gain in information in every step that I gain by getting the environmental information times the number of particles and the rate of exploration. So how fast do how many particles basically I consume in every step. Then, and in every step, I lose some information from the organism information times the rate of dissipation. So you get to a nice exploration and a balance between the exploration and dissipation. So the balanced rate of exploration, how fast does the organism explore the environment, we know because we know the basic the beta, the dissipation rate, we know the actual organism information, the environment signals the actual information from the environment, so the organism can decide on the minimal exploration rate that it needs to do to survive, to sustain, or to grow even more. So I'm saying the survival depends on adaptive exploration, and the organism control the exploration rate based on the dissipation. So they have some like minimal exploration to survive. And all it depends on is environment and the environmental information that is quantified by, for example, if you are in this point, you are in the desert, right? And you may have different signals from the environment that signal you how much information is there. So if you are in low environment or low information environment, you better move somewhere else or you better explore more, otherwise sooner or later you will dissipate, and I will show this in a few simulation graphs. So now getting to the simulation. So I have two scenarios, and in both scenarios I will let the fungi grow from the left bottom, create a subset of particles that it consumes from the environment, and let's see the total information of both scenarios. Again, I have just shown the desert here is really low energy, it's in equilibrium, so it doesn't bring any interesting information. And these white circles, we call it meadow. There's a lot of food, a lot of grass. So basically there's a lot of energy, it's far from equilibrium. I run both processes in every step. So in every step we see the changes in the information based on the dissipation and the increased number of particles due to exploration. And what we expect is to see a similar graph that Brooks and Weil suggested. A growing number of particles drives the growing maximum entropy, and there should be fluctuating entropy below, which helps us to see an idea of information, but it's calculated separately as a KL divergence. So now what we see is an evolution in 250 steps. the organism is set on a fixed path. It's not intelligent. You just let it go from left bottom to top right and back, right? So you don't see any logic in there. But I just want to see what happens if it fluctuates between desert and meadow. And whenever they enter a meadow, there is a green triangle. Whenever they exit a meadow and go to desert, there's a red triangle. So we should see increases of information between the green and red triangle, which is what we actually see with some fluctuations depending on the actual configuration of the particles. So here is the maximum entropy, the orange one. Below the dotted blue is the actual entropy. And the information corresponds roughly to the difference, the KL divergence. And here is zoomed in so we can see gradual increases in total information as the complexity of the organism grows. Because the alpha, the exploration rate, is set to be enough to compensate the dissipation. Another scenario which we wanted to show is that how does the organism actually die? How does the structure break down? So it's a different path. First it starts to accumulate information, and then the organism goes eventually to the desert and tries to commit a suicide. So I told him just go somewhere to the desert and let's see how does the information evolve. And this is what we got. We have similar growing maximum entropy because the number of particles is actually always growing. But the curves are actually not growing as scissors. Actual entropy and maximum entropy is not going far from each other. It stagnates, but it doesn't go down for the whole organism because it keeps some interesting information even through the dissipation. It's a random process. The dissipation never goes to the complete equilibrium, but it always fluctuates just a little bit near from the equilibrium. But when we look at the information per particle, then we can see that being in the desert actually decreases the information, and we can interpret it as a breakdown of individual structures of the organism. Because thermodynamic information is computed algorithmically, so it doesn't really know what structure breaks when. We can only interpret it as there is some threshold for the whole organism. So for example, if it goes below the total information, below some unit, the life actually dissipates and the structure breaks down, and we can interpret it as a death or decomposition of the whole body to smaller parts that do not maintain life. So this is my summary. So entropy and information can be detached. So information can be understood as a distance from the equilibrium, computed as a difference or KL divergence from the maximum entropy. And life could be, in this model, understood as regulating its exploration depending on the richness of the environment on information, which is related to free energy. And in poor poor environments, of course, it needs to explore more, and this could explain several different strategies that the organisms take depending on the
We can continue our presentation with two presentations online. We have two. Now we have Mr. Stefano Calzati.
Yeah. Can you hear me well?
Yes, we can start your presentation now. Thank you for your presentation. And we have 15 minutes max for your presentation. Thank you to respect time.
Yes, so I'm going to share straight away my slides. You should be able to see them now. 1 second. Yeah. So think that they made the discussion much more compelling. But I have overlapping duties at the Center for Advanced Study of the Joint Research Center of the European Commission where I work. Although here I put in the first slide that I am an independent scholar because this work I'm going to present is actually part of the work I've been doing as a researcher. I've been a researcher for 12 years now as a postdoc. So this work that I will present touches upon a few ideas that are more broadly discussed in the article that will appear in the proceedings. And as the title suggests, being as techniques, a quantum-informed conjecture on complexity, it's mostly a theoretical, philosophical work. I am a philosopher of science at core, and this work basically builds upon a book that I wrote together with media theorist Benguerir, which was published at the end of 2024 by MIT Press and is currently open access. And in this book, Quantum Ecology, we basically define ecology, we speak of an ecology as a system that has effect, but not causes, at least not causes in the ordinary sense of a direct link between causes and effect. So in the background of our discussion, we had in mind complex systems. And we identified mostly three ecologies in our book, and we call them technological ecologies. And by technology, we refer broadly to the Foucauldian and then Agamben sense of technology as a dispositive, which is material and discursive framings that shape a certain grasping of information. Or we also speak in the book an autopoietic sensing of reality. So just to unpack a bit of these ideas, the three technological ecology of sense-making that we identify, and I will discuss in a bit also what we mean by sense, are language, digital, and quantum. The language ecology is based on a meaningful word sensing, on the creation and sharing of meaning. The digital ecology, by contrast, is predicated on sheer computability, on the formatting of sensing into zeros and one, sensing as physical reality. And then we have the quantum ecology, which is based on a probabilistic world sensing, and we speak of synthetic sensing with the term synthesis, both in the sense of aggregation of different sensing sources, either biotic or non-biotic, artificial, and synthetic in the sense of artificial also. So the point to retain here is that across these technological ecologies of sense-making that we identify, there is always a partial ontological incommensurability. For example, large language model, which arise at the intersection of the language and digital ecology, create that kind of epistemological crisis that we discuss in the book and that we are witnessing nowadays when it comes to the production of knowledge as such. So, and then, as I mentioned, a bit of an overview, quick overview on what we mean, why we pick the word sense and sensing. Well, because at least in Latin derived languages, European Latin derived languages, although these can be extended also to logographic languages such as Chinese, sense is a heavily connoted term which has at least three connotations: direction, perception, and meaning. Sense as direction, sense as perception, and sense as meaning. So in a way then, sensing is always expressed perception plus cognition at the same time. And here it's worth mentioning the work by Kaufman, who makes the example of the bacterium, which swims through the glucose gradient, the sugar, because for the bacterium, the sugar matters. So in a sense, we are already in a form of sensing for the bacterium. And this also connects to what Atmas Bakker, who is by training a quantum physicist, speaks when he mentioned that meaning in this regard can be understood as a sixth sense modality for perceiving, for grasping psychophysical correlation. So in this regard, then, direction, perception, and meaning are constantly enacted through embodiment, and being always already entails sensing as embodied information processing, or differently said, sensing emerges as an informational I-word codetermination. So where does quantum comes in? Here I just mentioned three concepts that I discussed very quickly in the article, although in the book we also refer to other concepts: discreteness, entanglement, and complementarity. Well, discreteness sits at the very foundation of quantum mechanics, because quantum literally stands for packets of energy. Planck, at the turning of the 20th century, discovered that the energy emitted by the radiation of a black body was not emitted uniformly, but in packets. And then we have, of course, entanglement, the quantum unique effect phenomenon of quantum mechanics. And two particles are entangled when the measurement of one of them instantly affects the other. And in this regard, we also have the non-local feature of quantum mechanics compared to classical physics. And we have the principle of complementarity, formalized by Bohr in 1928. And Bohr himself speaks of complementarity in these terms. Evidence obtained under different conditions cannot be comprehended within a single picture, but must be regarded as complementary, by which he means mutually exclusive. So, in this regard, then Karen Barrett, who is also a trained quantum physicist, is the first one to put forward a non-epistemological understanding of complementarity, discussing how it is the whole act of observation that not only gives us certain knowledge, certain feature of a phenomenon, but determine the phenomenon as such. So the act of observation creates the feature of the phenomenon under observation. And just to give an example of this, there is the famous Wigner-Franz thought experiment, which was elaborated by Eugene Wigner, the guy on the right in the picture, and was in 1961 it was proposed, and then it was tested in a performing laboratory in 2019. So Wigner thought experiment it's very interesting because it exposes some inconsistencies. And the setup of the thought experiment is as follows. There is Wigner-Franz that performed the measurement of a particle inside a laboratory. Let's say that the measurement concerns the spin of the particle. So for Wigner-Franz, the measurement, as soon as it is performed, yields a definite outcomes, either spin up or spin down, and this is the famous collapse of the wave function. But for Wigner, who is outside of the laboratory and treats both the lab and the measurement that her friend performs as a whole quantum system, the outcome is not definite yet. It is still in a state of superposition. So in this regard, we have some kind of interesting consequences from a non-epistemological perspective. First of all, we have a sort of configurational realism, which basically attests that there is no observer-independent physical phenomenon. Different observers can assign different real states to the same system. And this, in a sense, will also bring us to have a relational epistemology, where two observers can hold complementary, which means mutually exclusive, but equally valid knowledge claim about the phenomenon at the same time. And in a sense, Frottier and Regner discussed this idea as a sort of nested recursive inconsistency at on the epistemological level, because if then we add a further nested level, let's say a Wigner-Franz who look at Wigner-Franz, then this is a kind of recursive inconsistency across different epistemological configuration. Having said this, where does complexity comes in? Well, I confess that when we were writing the book, I mentioned at the very beginning that we speak mostly in terms of autopoiesis. I was reading literature on complexity and complexity theory and complex system. And there is specifically an article by Jefferson and Heidegger in 2003 that really stayed with me. And in this article, they write that complexity is an issue of frame, a way of observing system, not an absolute class of systems. So in this regard, I've thought over the years that this idea of observation, this idea that complexity can be, for example, at a certain scale, but not at another scale, always looking at the same system, then if this is really a matter of frame, then I saw some resonances, some mirroring aspect with the issue of measurement. And John Wheeler himself claimed famously that if we extend, or cosmological extent, the trickiness intrinsic in quantum mechanics, then we basically derive the universe that is looking at itself. So in the article from here, I propose as a conjecture that complexity is a qubit, because the bits of information are entangled. Observer, observe, entangled. And just to give you a flavor of how the conjecture is built, I connect the idea of complexity as a way of observing and framing system to the notorious issue of measurement that sits at the core of quantum mechanics. So what is really measurement? And here I put three quotes. One is from Scott Armstrong, the guy on the right, who is a computer scientist, and the other two are from Thomas Hertog, a cosmologist who worked with Stephen Hawking also. And Thomas Hertog speaks of observership, which is really something that resonates with the idea of measurement. And in the first quote, Aronson speaks in a very tricky and interesting way. When you consider all the junk that might be entangling itself with your delicate experiment, and here he's speaking about the fact that quantum systems can keep their own entangled properties only when they are fully isolated, then it is as if the entire rest of the universe, Aronson claimed, is constantly trying to measure your quantum states. So really here we are in a situation in which measurements sit at the core of quantum mechanics, and this is also exactly what Thomas Hertog are right to claim when he speaks of the fact that observership, not much observation or observed phenomena, but observership is an agency operating at a deeper level to which physical reality comes about. And the universe is a self-organizing entity in which all sorts of emergent patterns appear. So from here in the article, they claim that embodied sensing can be understood as an agentic measurement throughout. We are literally agentic measuring devices throughout. And then I built up this conjecture by referring also to three dear philosophers of technology, Simon Stiegler and Nancy. And by reading them throughout, I realized that either directly or indirectly, they refer quite consistently to quantum aspect of quantum mechanics. And most interestingly, the three of them compensate each other blind spot. For example, Simondon, by maintaining mostly a cybernetic standpoint, claimed that information is not much a thing, but is more a kind of rapport. It's more of a tension between two disparate realities. So for him, then, being ontogenesis comes out of an information asymmetry between two disparate realities. The point here is, however, to extend this beyond the isolation of cybernetic system to reality as such. And Stiegler, in a similar way, posits a fundamental codependency between technogenesis and anthropogenesis. So in his theory, then, in his work, ontogenesis, especially anthropogenesis, is seen as a prosthetic, always as a prosthetic alternative. But there is no point in confining again this to human cloning, and rather it's worth trying to extend it to ontogenesis as such of reality. And this this is exactly indeed what Nancy does. He speaks of sense as the movement of being toward or being as coming to presence, which clearly define ontogenesis as an ongoing emergence rather than simply becoming. But Nancy is rather vague in describing how this emergence comes about, and this is where we can close the circle and referring back to Simon Don's idea of fundamental information asymmetry. So then, just to conclude, I articulated the conjecture in two parts. First, I kind of characterize what kind of being is at stake in ontogenesis, or better in ontoepistemogenesis, because it's always the two things always go hand in hand. And it's technical in the sense that anything exists, comes out of an information symmetry breaking. It is always already entangled. Informational embodiment exists as an I-word codetermination, and then it is always from within. And this again I refer to the idea of observership, or also the famous blind spot of science of which Frank and colleague speaks. So sensing, in a way, should always be understood as something that is already there and is already embedded in the coming into being of the I-word codetermination. So because it is always already situated, then it is also emergent and open-ended, meaning that ontogenesis happens rather than simply becoming, and happens in a non-predetermined way, or Kaufman would say in an unprecedented way. But how does this is enacted? Well, this is where I move beyond the book per se, and I speak not only of autopoiesis, but of auto/sympoiesis, and this slash should be understood as an ongoing complementarity, observer-dependent complementarity, of which we can always only embody one of the two sides at the same time. And just to conclude, to unpack a bit the nexus between complexity and measurement, from what I have discussed and also what I have actually described more in depth in the article, complexity is always already there as agentic measurement is. So paradoxically, in a way, closed systems are a of epistemological complexity. And every ecology, the three ecologies famously that I spoke at the beginning, are always already trans-ecological in a sense, meaning that their analytical framing, linguistic, digital, and quantum, is in the end an ex-post exercise in a way, which is observership-based and observer-dependent. It depends what kind of scale are we focusing on. So just also to give you some further look into the implication of this, beyond being simply a philosophical memory, such a discussion might open a closer dialogue between quantum mechanics and complex system modeling, especially of notoriously wicked problems of sustainability. And I also recently delivered a talk at the Joint Research Center on quantum-inspired policymaking, how quantum theory might inspire a different way of thinking and doing policy. And on the other way around, complex system theory might help inform an information theory-based interpretation of quantum mechanics and thermodynamics. Thank you very much.
Thank you, Mr. Stefano, for your presentation. Sorry, we don't have time to take a question. You can. Excuse, sorry, the organizer. We invite you to contact directly Mr. Stefano for the question. Sorry, Mr. Stefano. We continue with the presentation. Mr. Patrik, you are ready to present? You can share your presentation, please, and start your presentation. Thank you. We have only 15 minutes to close the session.
15 minutes, huh?
15 minutes, yes. share.
Almost there? You can hear me, right?
Yes, yes, you can start.
Yes.
Okay, so now you should see some slides. Is that correct?
Yeah, it's correct.
Okay, good. So,
It's
now
a good.
you should only see slides. Is that correct?
It's correct. It's correct. You can start.
Good. Okay, it's almost lunchtime, so I start in the kitchen. It's probably not the best idea, of course, but I just realized that. Anyway, so the story is that it's about complexity economics, and I quickly want to highlight just 2 things about complexity economics. Like in all complex systems, the phenomena emerge from local interactions. Very important is the second point here, agents behave and interact dynamically and in a non-homogeneous, heterogeneous loop. And that's now specific to the economy and was the first program of the Scientific Institute. That you get rid of assumptions like equilibrium and rational behavior of actors. So there are certain trends in agent-based modeling, so modeling the economy, and this talk is about one specific problem, which is the parallel computation of agent-based economic models. And so you can see these models get bigger and bigger, the fidelity increases as well, and there's a shift from qualitative to quantitative modeling. So there's 2 things that make our computation valuable. One thing is because of performance, and the other thing is that it more realistically represents actually what is happening in the economy. So in general, in complex systems, you have a lot of things going on at the same time, and this is also the case in the economy. And it's actually not so clear what is happening if we use computers in a serial way to compute our results. So there is a little bit of a gap that is quite underexplored. So before I give a perspective where this could go in terms of power computation of economic models, and I try to connect this with hardware, software, and complexity. So these 3 views, and I have to talk a little bit about hardware so you know where this is going. So first of all, this is how it looks. There's a CPU as memory, and you basically have to shift everything from memory into cache and cache into the CPU. And that's a bandwidth bottleneck. So that's a huge problem. Actually, it's very inefficient in any value you can think of. So that's the architecture down here. And on the right-hand side, what then also needs to happen is that everything you have in memory has to somehow nicely fit into these cache memory or cache lines. So the way you program it, if you program something that fits in nicely, you have that program, and if it doesn't fit, you get into problems. So there's a memory problem in just normal architectures. And if we look now at computer architectures for power computation, so these are SIMD and MIMD, so the layer 2, two models there. One says that you have basically one computation and you run it on all the data you have. That's the simple, and the other one is that you have different kinds of computations or instructions and you run them on different kind of data. That's mainly. And what you have today is usually like a mixture of the two in hardware. And you have a little bit of assembly and a little bit of memory. And so they're hybrid systems. So that's on the hardware side. On the software side, of course, you can use different software architectures to actually, implement bigger programs. And one thing I really would like to highlight here is something that is done in game development, which is called Entity Component System Architecture. And I highlight it because it allows you to improve the mapping of application into these cache lines I talked about earlier. So because it structures the program in different ways. So it's more data-oriented. So you have these entities, which are basically like just a number for any entity, or actor and agent-based model. And you have the components where all the data is, and then you have the system where the operations are, and that can run on these data components. And so this allows you to get a better mapping of the real world application because it's more data oriented as compared, for example, to object-oriented programming. Alright, now coming to the complexity economics perspective, so we start now at the beginning and put this together a little bit. So if you look at the economy, like in this image here, we have these actors, they interact with each other. There might be other sectors like politics, technology, science, and it's always more involved, more actors, and basically forming like this network. And what you could say is that, okay, so one thing is that these interactions is something we need to compute, but also inside each of these points here, so each actor is actually doing something. It's like, behaves in a certain way. It might just randomly left something, or it might learn something, so it has certain behavior. So there is two kinds of parallelism, inside and between the entities. That's the first point here. And the second point is that there is no control that would somehow orchestrate this. So it's self-organizing. So that's makes things more difficult for centralization and control of computations. So you need to have something decentralized in terms of power computation. So this complexity theory in a way gives you at least some hints to do if you want to do power computation, which is these two kinds of parallelism and decentralized synchronization. So we now go to the architecture or hardware perspective. And so what you could say is that so inside an entity, a single architecture is maybe something that is often useful, and combined with a view, where you can then basically go for the distributed person, so between the agents. View also has the advantage that it has this decentralized control. So there are systems like that, also very big systems, like here with this image. So this is the biggest chip you can have, actually. It has 4 trillion transistors, 900,000 cores. It has 34 gigabyte of memory on the chip itself. And it basically has like a little, it's a multi-machine that has different SIMD processors on it. So it's a combined machine on one chip. And these are the kind of hardware innovations that I think complex systems models can profit a lot because they use this kind of new kinds of, they can make use of these new kinds of products. So there's another trend which is called processing in memory. So this goes in that direction, so we move basically the CPU or the processing, we move closer to the memory. So afterwards we do something similar, this one is a little more extreme. And there's even the crazy approach where you use the DRAM, for example, itself to do computations. So that's on a more experimental side, but there are some developments, and I think this will change quite a bit because it kind of gets rid of that bottleneck moving the memory, and it's also better aligning with the application of complex systems. In terms of programming, so this ECS architecture for the development really helps to get these data streams better into memory. Then, in terms of programming, there's things happening that give you more control when actually programming that. So, because programming the details, they still matter. It's not just the hardware, you also need to program it in a way that it is supposed to work, so getting from basically from the application to the hardware. And there are some frameworks around that help you do that. So there's a little bit of automation, there's compiler practices, there's all the areas, so that people from the application can actually use frameworks to do that. So I have to summarize this, run through this a little bit more quickly. And so there are 2 points. These hybrid systems, they capture at least some of the parallelism. And if you can actually do the processing in memory, that would be more suitable because you don't have to move around. So you can map your application better into the hardware. On the software side, there are some architectures, software architectures that help you optimize the memory. And also on the language side, with C++ and newer things and runtime systems like HBase that give you some control to actually implement these things. And yeah, so that's overview. I'm not sure we have a little bit of time for questions.
Thank you. Thank you, Mr.